So now for something completely different. So we're not going to talk about RISC-V very much here, but it is related. So I'm from DARPA, so we fund research. And so I'm going to talk to you about some programs that we're doing right now that are intended to reduce the cost and complexity of design, right? So if we go back to the beginning of chip design, right? 1947, first transistor at Bell Labs, Shockley and his team, right? They came up with an amazing discovery. 3 people were, credited, but maybe 12 people were working on it. And those were the good times, right? Today, to come up with a new device, you're going to probably spend billions of dollars. And so, 70 years forward, we create incredibly complex chip designs. I mean, these are marvels, 20 billion transistors. This one is from AMD. You could have put up NVIDIA or Intel here as well. But 20 billion transistors, 20 miles of wiring. But there's a backside, right? You need like 500 people, maybe $500 million to do this. Not everybody can do it. And this is really putting a bottleneck on what kind of chips we can design. So how do we get here, right? So everything we know today is driven by economics, Moore's law, right? You keep reducing the cost per transistor, you ship in higher volume, and somehow magically the revenue for the semiconductor industry keeps improving year over year, every year, even though we sell more for less every single year. And the way we do that is we don't really worry so much about NRE costs, design costs, because we make it up in volume. So this is why I came to DARPA. So I used to work for a small startup, and looking at design costs was paramount, right? I was not Intel. And so the question is, if the NRE cost, the design cost, is reduced to 0, what can we do with that? So that was the question I came to answer at DARPA. And so, for those of you who don't know what DARPA is, DARPA was set up in 1958 as a response to the Soviet Union's launch of the Sputnik, which was a huge surprise. Scared bejesus out of the United States Department of Defense and said we never want to be surprised like that again, right? So we need a research agency that avoids surprises, and it has had some very big successes. So the internet, we claim we invented the internet. Just so you know, it was not Al Gore, it was us, and I think there's definitely some validity to that claim, right? Because there was a continuous investment from the 60s to the 70s, the ARPANET, the first network topology, TCP/IP, the protocol, which is still in use today, can trace its roots back to DARPA. And I think we can all agree that, where would we be today without the internet? This is a profound addition to society, and DARPA definitely gets at least a credit for that. Take something else that is truly profound today, GPS. Right? Where would we be without GPS? Well, many people would be lost, that's for sure. And so in the late 80s, there was a miniaturized GPS program started with DARPA, and that's a pretty clear lineage as well. More recently, in self-driving cars, DARPA really kickstarted this next stage of autonomy, right? With a couple of grand challenge programs, and you can see today a big chunk of the workforce that are really the leaders in autonomous drive can be traced back to these DARPA grand challenges. And today, since we're talking about RISC-V, there were a couple of programs, the PERFECT program and the POEM program. PERFECT was a high-efficiency computing program. POEM was an optics program. And it was not a goal to stand up an open-source architecture, but the Berkeley team had enough freedom to innovate. And they decided that, we're going to invest a lot of effort and resources in creating this platform. And so if you look at RISC-V, right? So this is a statement from one of the technical reports from Berkeley. DARPA was the #1 funder for RISC-V development at Berkeley. So we like to think that we had something to do with standing up RISC-V as well. So my question when I came to DARPA 2 years ago was, why can't we have this for hardware design? We have it for software. We take it for granted. I mean, where would the world be today without the compilers? What if we still had to write ones and zeros? What if we had to write assembly code? We wouldn't be very productive, and the range and complexity of the products we could design in software would be limited. So that's what I want for hardware. I think we all want something like that. And so this year, there's something called the Electronics Resurgence Initiative. It's a $1.5 billion effort out of DARPA, and it officially kicked off this summer in San Francisco. So this is my program. It's a $100 million program to build a true silicon compiler. And it's got two main components. It's got the layout generation, so you feed it analog schematics, you feed it Verilog code, and it spits out GDS2 ready for production. That's the goal, at least. And then you also have the standard libraries. This is the open source part. So a compiler, C compiler, or any other compiler wouldn't be very interesting if you didn't have a rich library that you can draw on, because otherwise you'd have to write every line of code from scratch every time. So this is about a $65 million, $35 million mix. And we got an incredible team working on this, 22 entities in total, well over 200 researchers, split between academia and commercial. These guys started working in June. They're about 6 months in, and a lot of great progress so far. So I'm not going to steal their thunder. You're going to hear a lot more from these teams over the next 4 years. But I will touch a little bit about one effort that is especially exciting. So you know, what is the idea here, right? So today when we do layout, we're not talking about front-end design. You still have to write your own code. But once we have the Verilog and schematics, how do you turn that into a product? And so today, there's a lot of expertise that goes into knowing how to tune the power grids, how to close timing, how to do floor planning the correct way. And unless you have that expertise, you really can't do a chip today. And so, and it's not just about chip design, it's also about package design, it's about board design. And in each domain, you have these siloed experts that take care of it. And the times are long, 9 months, 3 months. So the question here is, can we take that expertise and can we codify it? But of course, it's 2018. We're not going to codify it with expert system and write a rule down for everything. That would be very 1999. Today, we're going to use data. There are maybe 5,000 tapeouts done every year. There is plenty of data, not necessarily easy to get access to that proprietary data, but the data is there. And so we are going to try to extract all those corner cases out of the data to stand up an intelligent or machine learning silicon compiler that will address chips, packages, and boards within 24 hours. So this is a pretty tall order. And one of the teams doing this is UC San Diego. So this is Andrew Kang, Professor Kang, working with Brown, UT Dallas, Michigan, and Minnesota on the academic side, and Qualcomm and ARM as design advisors. And I mean, it is exciting, right? This is a free and open source compiler, start to finish. It is an incredibly ambitious software engineering project, especially for academia. I mean, what saves them is the fact that Professor Kang and others have been in the EDA research industry for 30 years. And they've created a lot of the algorithms that we now use in commercial tools. So that's the great part. The bad part is there are now students writing code, right? So there's going to be some ramp up. So I would say that one of the reasons I want to be here today is that anybody who thinks this is a noble goal for this community, step forward, right? We take any contributions. It's up on GitHub already. And I'm sure Professor Kang and others would appreciate the help and the feedback. So now we have a compiler, right? We have Verilog or analog schematics to GDS2, but what about writing the code, right? Software verification and design is a big part of the $100 million budget that we take for granted today. So how can we improve that? So in hardware, we kind of have a two-layer system, right? We have the IP layer, where we license things from ARM or Cadence or Synopsys. We have EULAs that restricts movement and modification and sharing. So that's kind of make a two-layer system. In software, we have an infinite layer system, right? We can modify, we can share freely. We have the FOSS principle, and then you can reach much further, right? You can truly stand on the shoulders of giants instead of trying to be a giraffe every time. So I think it's time. It's time we have something like the open source ecosystem for hardware. So that is the POSH open source hardware program. So there's a few different components that people are working on that I'm going to highlight today. The first one is a multi-core cache coherent RISC implementation in order. So you've seen a few of these floating around now. What's a little bit different about this one, and this one is run by Michael Taylor out of University of Washington, is that it's designed for a community. So he's actually tried to create interfaces, internal interfaces that you can plug into within this architecture. So there's going to be a GitHub repository with an example implementation, clearly defined internal microarchitectural interfaces that people can plug into. So imagine plugging in your own cache subsystem or plugging in your own FPU. So he's trying to provide very clear API hooks into the microarchitecture to create a community-driven Linux for RISC-V. Another one is kind of the encore piece, right? What do we do about the PCI Express, the gigabit Ethernet, the 10 gig, the USB? We need those components as well in this program. Second or third, we talk about taking IP. I know I've had this problem in the past. I would go up on GitHub or open cores. I would look at a Verilog core, and I would never be comfortable enough to use it in a product. I would never trust it enough. So how do you take some code that you have not designed and trust it? If we take it from ARM or Cadence or Synopsys, we pay for it. There's a certain guarantee and a warranty. Open source code, there is no warranty. It's you get what you get. And so how do we trust it? So the verification tools here is very key. So Clark Barrett and Subhashish Mitra at Stanford are working on formal analysis tools that are scalable. And these are some of the leaders in that field academically. So I'm very excited about their work. I already got a demo of it where they took one of the classic bug examples, an asynchronous FIFO, and demonstrated there was an issue with it. And so I think something like that is exciting to have in open source hardware design. The fourth one, also very exciting for somebody like me who is not an analog designer. I'm a digital designer. So whenever I would have an analog circuit, if I didn't have an analog designer, I couldn't include that in my product. So after this program is done, there's going to be a rich catalog of analog circuits up on GitHub that you can leverage, meaning PLLs, DLLs, data converters, temp sensors, PMICs, all of that is going to be available open source. It will probably not be as good as something you can get as an IC from TI or ADI or even an analog IP vendor, but it's going to be good enough for many of you. So I think that's very exciting in terms of enabling new systems for people who are not analog designers. Fifth, we have 3 teams working on open source FPGA implementations. So the idea is that for a security perspective, sometimes we do not feel very comfortable in taking FPGAs that are opaque, that are incredibly complex. There could be hardware Trojans, not known in Trojans, but backdoors that nobody knows about and we don't know about. It's better to have open source implementations. This is based on the VTR toolchain and then custom FPGA architectures underneath. So the 3 teams working on that are going to have a standard implementation. This is Princeton, Utah, and MIT. And then finally, a goal of this is to set up an open source culture of sharing, which, having been at DARPA now for 2 years, I found that it's definitely an uphill battle. And with the RISC-V Summit, I see more people who get it here than other places, but it's going to take a while, just like it took a while for software as well. Somebody, it was Ballmer, I think, at Microsoft, who said at one point, open source is a cancer, right? And then today, of course, we know where Microsoft is. It's embracing open source with open arms. So it takes a while to really get it. Open source is not evil, that's for sure. So if you want to track the progress, most of these things are going to be completely open source and up on GitHub. There's already a bunch of stuff up there. And in terms of schedule, the first integration exercise is going to be in January. So we're going to bring the 200 people, mostly students, who write the code and test the code. They're going to come together in San Diego for a week-long integration and hackfest. By June next year, we'll have a kind of a alpha release that will probably work pretty well. At 2 years, we will have a tool chain that can actually be used to tape out chips. So you can take, if you have Verilog code at 14 or 16 nanometer, you will be able to ship a GDS2 through Moses or TSMC or GF. And then after the full 4-year program, our goal here is to reach parity with human teams. And if I look at the history, I see this as similar to where GCC started out in the 80s with Richard Stallman, right? Initially, it was the free version that was not as good. And eventually became the go-to version that was good enough, or sometimes even better than a proprietary compiler. So that is the goal for this. So what? So now kind of a little bit about the disruptive part. And I think this is not an incremental thing. Going from partially automated or fully automated is a binary switch. And so I want to talk a little bit about why I think it's very important and why I think it could be really a game changer. So the first thing is we've seen this explosion of design costs for $100 million, $500 million. One day there will be a trillion transistor chip, right? And if it continues at the current curve, that's going to cost $5 to $10 billion. So that's going to kill Moore's law. So we're going to have all these transistors that are available to us from a manufacturability standpoint, but we cannot design to them because it's going to be too expensive. So the way I see it, on the left here we have the kind of the current model, which by the restrictions of the ULAs, we really can't have a very deep stack, right? So we're limited to something like, for a trillion transistors, right? 100,000 blocks, each block, let's say, being 10 million transistors, because that's all a single person can wrap their heads around. That's all you can really place and route. So you get this really weird hierarchy that is not manageable. Versus a very hierarchical architecture, where you kind of have this radix nested doll approach that you probably can reach 1 trillion transistors. So if you think of kind of comparing this to software, the right model is a software approach today. Nobody tries to generate a trillion lines of code or a billion lines of code flat. Right? You have to use hierarchy. Second, if we look at specialization, this is one of these things that I've lived now for 20 years doing DSP architectures, computer architectures. Flexibility costs something, right? I would say that run away from any person who tells you that you can have flexibility and energy efficiency at the same time, right? That's not going to happen. So I take this as a fact that there are some applications that are only achievable if you specialize. So if you design an ASIC for it, that's the only way. So, but of course we know, right? You've seen this curve before, right? This is our dilemma for the industry. Things have gotten so expensive that you can never get a positive ROI on an ASIC when you're spending 10, 20, $100 million, unless you're shipping 1 million chips. So there are these unreachable applications. It's fairly large, right? It's kind of a long tail where we'd like to design them. They would have value to have a chip like that. It would enable something new, but we can't do it because we don't have that kind of money. So this is my disruption space. So you see the blue curve there is kind of like you have a minimum cost, right, driven by EDA costs, by licensing costs, by tape-out costs. And even for a unit of one, you're going to spend that $10 to $20 million. Well, if we do some things, right, for example, if all the IP is free, if the compiler is free, so kind of like an open source approach, you have GCC, you download something from GitHub, and now if we have an enormous volume of opportunities, now we can actually make much better use of the silicon tape-out cost. So even today we have MPWs, but we can't fill those MPWs because the cost of EDA tools and design. But the reticle of 700 square millimeters, if you only want 1 million transistors, which is is much bigger than the initial processors people used to design. If you only want 1 million transistors, that share of that mass cost, which could be a couple of $1 million, is not very much. So for 1 million transistors, it turns out that you can get a unique chip that only exists as an n is equal to 1 chip in the world for $500. That is eye-opening, right? So not $20 million, not $10 million, right? With these caveats, you can have a 1 million transistor chip for $500. So what could you do with a 1 million transistor chip? What kind of functionality could you achieve? So if we say for a CPU, maybe it's not very much. For an ASIC, if every one of those transistors is used perfectly, that's a lot of compute power. So now we take that concept, right, and we look at what we have today. What has been done already in terms of automation? Well, if you look at a 300 millimeter fab today, it's fully robotic. There are no hands that touch the wafers in the flow. They kind of load it into a FOUP in the beginning. They take the FOUP, the pod out at the end, but in the beginning, it's all automated. There are these tracks that run there up ahead, and there are jobs that get distributed. So we have that. In the middle, we have the compute, AWS and Microsoft and Google Clouds. Nobody's running around loading CDs with distros, right? It's all automated. It's all through DevOps. But here we have this layout of army of chip layout engineers, right? And that, it turns out if you actually remove that army, then we can go end-to-end automation. We can do fully silicon, Verilog code all the way to chip automation and truly have a factory. And the way I look at it, if we remove that constraint, we democratize access to silicon technology. That 300 millimeter fab is so efficient today that you can actually get in there as a fairly small customer if you can reduce the cost of interaction with the TSMC and GF to zero. And of course, we trade off human time, which is finite, for machine cycles, which is almost infinite. So as a result, we have this new paradigm where we can actually customize for n is equal to 1. And which means that if you take a wafer like that, you can actually take a very, very small piece of it, and you'll own that part of it. And you pay per square foot, basically, or per square micron. So now, what can we do with that, right? What are some interesting cases for n is equal to 1? And this is just me kind of noodling and thinking out of the box, but people can be more innovative and come up with much cooler applications than this. But there's a DARPA program called N0, which has to do with very, very low energy, battery-less or long lifetime applications. And when you look at battery, it doesn't really improve very fast with time. So you have certain envelopes, right, depending on the size that you have to fit into. So that's a scenario where, well, if the CPU can get you here, an ASIC can get you 1,000 times further. That's a big deal. So that's an area where I think we could, if we start thinking about what can you tune an ASIC for, what can you tune a machine learning network for, this is one of those areas where energy matters. So this is like a prime IoT scenario, where today we can do certain things by having programmable devices, and we should want to ship those in the millions or billions. What if you fill a reticle with unique devices, each one for a very small number of units? Another one is size constraints. So the physical world around us does not change, right? Our blood cells, our human body, everything around us is fixed in size. And so we have to be able to fit into that. So one way that you can say we've done that is by scaling down. So today, I'm pretty confident that at 3 nanometer, you can fit the original Intel processor inside a red blood cell, which is pretty crazy to think about. But what if you can have 1,000 times more performance than that? Well, you can still only have 2,300 transistors, but it would be 1,000 times more powerful than that thing you see there. And finally, my favorite application, right, for customization and individuality, there's over 7 billion individuals on Earth. What if each one of them had a chip, right? If a million transistor chip only costs $500, what can we do with that application, right? Each one of us has unique DNA, unique age, physiology, history, right? Security profile. Can we design $500 seems like a lot of money, but when healthcare per person for a year is $25,000 fully loaded, doesn't seem like a lot. So I think there's a lot of opportunities for customization and specialization if we can reduce the cost of design as close to zero as possible. I hope I convinced you that having a silicon compiler can be kind of disruptive, and please track the program. I think there's going to be some great stuff coming out of it. So thank you.